Hello students, I am Mrs. Gauri Shankar Bhor from Ferguson College. Today we are going to study some points from the superposition of wave chapter number 6 from the physics textbook. Already we have studied few points in the last lecture, but in today's lecture we are going to study equation of a stationary wave, different properties of stationary wave, what is free vibration, what is forced vibration, what is harmonic and overtones, and what is end correction of the wave. Let us move to PPT now. Equation of stationary wave on a stretch string derivation. In this derivation, consider two waves of same frequency and amplitude traveling along a long uniform string but in opposite directions. Now we know 2 pi upon lambda is equal to k, that is the wave number. 2 pi n is equal to omega is the angular frequency. Now equation of wave traveling in positive x direction is given by equation y1 equal to a sine 2 pi nt minus x upon lambda. Equation of wave traveling in negative x direction is given by equation y2 is equal to a sine 2 pi in the bracket nt plus x upon lambda. Now due to superposition or due to interference of these two waves, we get principle of superposition. By using same principle, we get resultant displacement of particles of string, that is y is equal to y1 plus y2. Substituting y1 and y2 equation in this resultant equation, we can write y is equal to a sine in the bracket 2 pi in the another bracket nt minus x upon lambda plus a sine into the bracket 2 pi in the another bracket nt plus x upon lambda. Now solving this equation by using trigonometric formula sin c plus sin d. Sin c plus sin d is equal to 2 sin c plus d upon 2 into cos c minus d upon 2. So by applying this formula to this equation, we get after solving y is equal to 2a sine 2 pi nt into cos 2 pi x upon lambda. This is equation number 1. Now using 2a cos 2 pi x upon lambda is equal to a in equation 1, we can write y is equal to a sine 2 pi nt. Now omega is equal to 2 pi n. So substituting omega in this equation, that is in y equation, y is equal to a sine omega t. Now this equation does not contain term x upon lambda. So this equation does not represent progressive wave, but this is the equation of a stationary wave giving resultant displacement due to superposition of two waves traveling in opposite directions. Now the amplitude of the resultant is given by 2a cos 2 pi x upon lambda is equal to a. Now in amplitude expression there is x term or x upon lambda term, so which shows that it is the periodic function of x, that is amplitude is varying periodically in space. Now there are some significant points on the string which show very minimum displacement, that is their amplitude is minimum, that is 0. So we can write in amplitude expression a is equal to 0. So we can get 2a cos 2 pi x upon lambda is equal to 0. Now we get amplitude 0 when cos values are 0. When we'll get cos value 0? When cos angles are pi upon 2, 3 pi upon 2, 5 pi upon 2 and so on. Now these angles we get when particle positions are, that is x is equal to lambda upon 4, 3 lambda upon 4, 5 lambda upon 4 and so on. So generalized equation of this is x is equal to 2p minus 1 in the bracket into lambda upon 4, where p is equal to 1, 2, 3 and so on. Now there are some significant points on the string which show maximum displacement. Those points are called antinodes. So the antinodes are the points of maximum displacement. Now the displacement is maximum, that is plus minus 2a. This we get when cos values are maximum values, that is extreme values of cos. cos extreme values are plus or minus 1. So these cos extreme values we get when cos angles are 0, pi, 2 pi, 3 pi and so on. These angles we get when particle positions are x is equal to 0, lambda upon 2, lambda, 3 lambda upon 2 and so on. Here in this case we can observe when particle position here x is equal to 0, there is antinode is formed. So the antinode is formed at the origin. Now in the equation of stationary wave, when sin omega t is equal to 1, then we get at that same instant of time when cos kx is equal to plus 1, for the particles they will show maximum displacement in positive direction. Now at the same instant of time, all the particles for which cos kx is minus 1, they will show maximum displacement in negative direction. Now when sin omega t is equal to 0, then particles, all the particles, they will cross their mean position. Some of them then move in positive direction, some will move in negative direction. Now if you observe positions of nodes, here these are the successive positions of nodes. Distance between them is lambda upon 2. Similarly, if you observe successive positions of antinode, distance between them is also lambda upon 2. So here finally, now we can say distance between two successive nodes or antinodes is equal to lambda upon 2. But if you observe first node position and first antinode position, this is the successive position of antinode, then distance between them is lambda upon 4. Similarly, second position of node and second successive position of antinode, again distance between them is lambda upon 4. So we can conclude distance between a node and an adjacent antinode is lambda upon 4. So students, so far we have studied what is transverse standing wave. Now let us study longitudinal standing wave. Now in this case, first figure showing that the piston is moving at one end of the pipe, which is closed at its another end, and inside the pipe there is longitudinal standing waves are produced. Now second figure is the displacement waveform. Third figure is the pressure waveform. Now consider two dots, two red dots in this longitudinal standing wave. Now first dot is the stationary dot. This dot, it is at displacement node position. Now when the medium particles, when they come close to each other, we know in case of longitudinal wave, medium particles, they oscillate parallel to the direction of propagation of energy. So when these medium particles, when they oscillate and when they come close to each other, they get compressed and compression is produced. In this region, pressure increases to its maximum value. So on this pressure curve, here we can get from this mean position to this maximum, here pressure value increased. Now when these medium particles, when they are separated from each other, then rarefaction is produced and pressure decreases to its minimum value. So at displacement node position, compressions and rarefactions, they are alternately forming and pressure antinode is formed. So at this point, pressure antinode is formed, which we can see, which we can observe on this pressure waveform. But if you observe this moving dot, moving red dot, which is showing that the moving particles of the medium, this is the dot which is at displacement, this is the dot which is at antinode displacement position. So this dot is moving, showing that medium particles are also moving. So there is no change in the pressure. So therefore here the pressure node is formed. So in this case we can observe there, due to the variation in the pressure, the form is formed. Now there is a phase difference of pi radian between displacement wave and pressure wave. Now we have observed that in case of transverse standing wave, because medium particles, they oscillate parallel to each other. Even though they are oscillating perpendicular to the propagation of energy, but they are oscillating medium particles, they are oscillating parallel to each other. So no change in the pressure. Therefore, pressure waveform does not form in case of transverse standing wave. Next is properties of stationary waves. This is a diagram showing stationary waves which are produced along the length of the string between two fixed ends, nodes and antinodes. They are formed along the wave. First property, two identical waves, either transverse or longitudinal waves, traveling through a medium along the same path but in opposite direction. Second property, in transverse stationary waves, that is when two identical transverse waves, when they superimposed, then transverse stationary waves are formed. Now some points are motionless called nodes and some points are oscillating with maximum amplitude are called antinodes. Now in between node and antinode, different points, they are oscillating with different amplitudes between 0 to A. Third property, in a longitudinal stationary wave, that is when two identical longitudinal waves, when they superimpose, then longitudinal stationary waves are formed. But here in this case also, points at which the amplitude of the particles of the medium is minimum are called nodes, and the points at which the amplitude of the particles of the medium is maximum are called antinodes. In between node and antinode, all the particles, they oscillate with different amplitudes between 0 to A. Next property is the distance between two consecutive nodes or antinodes is lambda upon 2. This point already we have discussed in the earlier slide. Now the distance between a node and an adjacent antinode is lambda upon 4. This point is also already we have discussed. The amplitude of vibration varies periodically in space. All points vibrate with same frequency. So string also vibrates with the frequency omega, which is same as that of the progressive wave. Though all the particles possesses energy, there is no propagation of energy. The energy is localized and velocity is 0. All the particles in the same loop are in the same phase of oscillation, which reverses for the adjacent loop, and therefore all the particles of the string, they pass through the mean position simultaneously and twice during their each oscillation. Now comparison of progressive waves and stationary waves. First point, in a progressive wave, the disturbance travels from one region to the other with definite velocity. In a stationary wave, disturbance remains in the region where it is produced. Velocity of the wave is 0. In progressive waves, amplitudes of all particles are same. In stationary waves, amplitudes of particles are different. Third point, in progressive wave, the particles do not cross mean position simultaneously. Third point, in stationary waves, in a stationary wave, all the particles cross their mean positions simultaneously. In progressive waves, all the particles are moving. In a stationary waves, particles at the position of the node are always at rest. Energy is transmitted from one region to another in progressive waves. In stationary waves, there is no transfer of energy. In a progressive wave, phases of adjacent particles are different, whereas all the particles in the same loop are in the same phase of oscillation, which reverses for the adjacent loop. So these are the points in comparison. Next point is free vibration. Now the frequency at which body tends to vibrate or oscillate when it is hit, plucked or somehow disturbed from its mean position, then it is called as natural frequency of the body. Now this natural frequency depends on the dimensions of the body and the elastic property of the material of the body. When the object is displaced from its equilibrium position, then restoring force acts on that body, which keeps the body in vibrations. So such vibrations are called free vibrations. For example, if a simple pendulum is displaced from its equilibrium position, then it vibrates or it oscillates at its natural frequency. Strings of the musical instrument, if they are plucked at its any point, then they also perform free vibrations at their natural frequencies. Then prongs of the tuning fork also perform free vibrations at their natural frequencies. So in free vibrations, once the body is displaced from its equilibrium position or from mean position, it performing free vibration, but afterwards the force is then removed. Now the amplitude of free vibrations goes on decreasing due to the frictional resistance of the surrounding medium. In this case, the body loses its energy, vibrations eventually stop, and body afterwards comes to rest. So in words we can say, the frequency at which an object tends to vibrate when hit, plucked, or somehow disturbed is known as its natural frequency. In free vibration, the body at first is given an initial displacement and the force is then withdrawn. The body starts vibrating due to restoring forces acting on the body and continues the motion on its own. So example is simple pendulum pulled aside and released. So observe this animation. In this, when the pendulum is released from its one of the extreme sides, then restoring force act on that pendulum. Now in this case, in this animation, the component of gravity acts on that pendulum towards the mean direction or towards the mean its position, and therefore that keeps body in free vibration, which vibrates at its natural frequency. Next point is forced vibration. In forced vibration, when an external periodic force is acting on the body whose natural period is different from the period of the external applied force, now the amplitude of force vibration depends upon the difference between the natural frequency of the body and the frequency of the external periodic force. If this difference is small, then the amplitude of force vibration is maximum or large. If this difference is large, then the amplitude of force vibration is small. But if two frequencies are matched, that is the frequency, natural frequency of the body and the frequency of the external periodic force, if are the same, then it is termed as resonance and we get maximum amplitude in these forced vibrations. Now, for example, string or the air column can undergo force vibration if the source of sound, like the vibrating tuning fork, and its frequency, if it matches with the frequency of the system, then resonance is said to occur and we get a louder sound. So in words we can say, an external periodic force is applied on a body whose natural period is different from the period of the force. The amplitude of forced vibration depends on the difference between the frequency of external periodic force and natural frequency of the body. Smaller the difference, larger the amplitude. If the difference is 0, it is termed as resonance. Now in this animation, we can observe this stick strikes the first tuning fork and it vibrates. First tuning fork vibrates, and due to forced vibration, this ball which is tied to the string and from the fixed support it is suspended. So when the energy is emitted from this first tuning fork which is vibrating, that energy is absorbed by this ball, and due to forced vibration it also oscillates. It is due to forced vibrations. Next point is harmonics and overtones. Depending on the boundary condition of the system from where the stationary waves are reflected when they are set in the system, that is string or an air column, which produces the possible wavelengths or frequencies of vibration of the system. These are called the natural frequency of normal mode of vibrations. The minimum of these frequencies is termed as the fundamental frequency or the first harmonic. So if n is the fundamental frequency or the first harmonic, the frequency of second harmonic is 2n, third harmonic is 3n, and so on. Thus, the fundamental frequency and all its integral multiples are called harmonics irrespective of whether they are actually present in the given sound or not. Now the term overtone is used to represent all higher frequencies. If n is the fundamental frequency, then first higher frequency we can say first overtone, then second higher frequency after the fundamental is called second overtone, and so on. So the overtones are only those multiples of fundamental frequencies which are actually present in the given sound so produced. So but harmonics may or may not be present in the given sound. Next is end correction. Now if an air column is made to vibrate in a pipe closed at one end or open at both ends, then the antinode is formed at the open end because the medium particles are free to vibrate maximum here in comparison to the medium particles inside the pipe. So the antinode is formed at the open end and a node is formed at the closed end because the medium particles are hardly free to move. So the node is formed at the closed end of the pipe. Now this antinode is not formed exactly at the open end of the pipe, but it is little beyond the open end of the pipe. Here the medium particles at the plane of the open end of the pipe, they are not free to oscillate, they are not free to vibrate in all directions. So the reflection takes place at the plane of the open end of the pipe. So this distance between the open end of the pipe and the position of the antinode is called end correction. So in words we can write the distance between the open end of the pipe and the position of antinode is called the end correction. According to the Reynolds, to the first approximation, the end correction at an end is given by E is equal to 0.3 into D, where D is the inner diameter of the pipe. Now in laboratory, we find this small d, that is the inner diameter of the pipe, by using vernier caliper instrument. And after multiplication, this multiplied answer, if we get up to second decimal place, we round it off up to first decimal place. And because we measure always length, we always use length to we always use scale to measure length, and least count of the scale is 0.1 centimeter. So therefore we round it off up to first decimal place. Now for a pipe closed at one end, corrected vibrating length of an air column, that is capital L, is equal to L plus E, where small l is the length of the pipe and E is the end correction at the open end of the pipe. Now for a pipe open at both ends, corrected vibrating length of an air column, capital L, is equal to small l plus 2E, because in this case two antinodes are formed at two open ends of the pipe, and therefore two antinodes and there are two end corrections at two open ends of the pipe, and therefore corrected length of an air column, capital L, is equal to L plus 2E. Next point is, consider a pipe closed at one end. Now here pipe consists of air column inside it. When the source of sound, like a vibrating tuning fork, if is held at the open end of the pipe, waves are sent inside the pipe. These waves, they are reflected from the closed end. Now the phase of the reflected wave, that is the phase of the longitudinal wave, depends upon whether the end of the pipe is closed or open. Also, it is also depends upon the how wide or narrow the pipe is in comparison to the wavelength of the longitudinal waves. So, as the diagram shows, this is the fundamental mode. In this case, antinode is formed at the open end because the medium particles are free to vibrate more in comparison to the medium particles inside the pipe. So, antinode is formed at the open end and the node is formed at the closed end as the medium particles are hardly free to move. So, at the closed end, node is formed. Now, diagram shows this is the simplest mode of vibration of air column closed at one end, known as the fundamental mode. Now in this case, the length of air column, that is capital L, is equal to lambda upon 4 and lambda is equal to 4L. Now lambda is the wavelength of fundamental mode of vibrations in air column. N is the fundamental frequency. Now we know velocity of the wave equation, V is equal to N into lambda. So fundamental frequency N, we can write it as V upon lambda. Already we have written here lambda equation, that is the lambda is equal to 4L is got. Substituted in the denominator, we can write V upon 4L. Now we know corrected length of the air column is equal to L small l plus E, where small l is the length of the pipe and E is the end correction which is formed at the open end of the pipe. So corrected length, therefore L plus E. So therefore fundamental frequency, we get V upon 4 in the bracket L plus E. Now the fundamental frequency is also known as the first harmonic. It is the lowest frequency of vibration in air column in a pipe closed at one end. So in today's lecture, we have studied what is stationary wave, what is the equation of the stationary wave, different properties of the stationary wave, then what is free vibration, what is forced vibration, what is harmonic and overtones, what is end correction of the wave. Also we have studied vibrations of an air column in a pipe closed at one end, and in this also we have studied what is fundamental mode of frequency. Thank you.